Good evening. Welcome to the session 4 of Parabola. In the last session, we had discussed about the properties of focal chord. We will continue discussing the properties and then some more uh, things about focal chord before moving to the tangency part. So let's solve this question. So PSQ is the focal chord of parabola. Y square is equal to 8x, so that PS is equal to 6, and then the length of QS is required. So we know that if I have a parabola here, and this is my focal chord P, Q, and this turns out to be S, then we know that semi-latus rectum is the harmonic mean of SP and SQ. So that is 1 over SP plus 1 over SQ is equal to 2 over semi-latus rectum. So semi-latus rectum is 2A basically, so this case is simply 1 over A. So I have here 1 over SP turns out to be 6 plus 1 over SQ is equal to 1 over A. A I need to find out. So you have 4A is equal to 8. So from here you get A is equal to 2. You can just plug in here A equal to 2. So now I want 1 over SQ. This turns out to be half minus 1 over 6. This is 6 minus 2. You can take the LCM if you want. So this turns out to be 4 over 12, which is 1 over 3. So from here we get QS is equal to 3. And this completes my problem. So here we have solved this problem just by using a simple property. Now, let's go ahead and we'll do some more. So this is property number 4 in the row, which turns out to be what? So circle drawn considering focal length as diameter touches the tangent at the vertex. So circle drawn considering focal length as diameter touches the tangent at the vertex means what? If I take any point here, this way, suppose this is my parabola, and I take any point here. So from this to this is my focal distance. That's what it is saying. Focal length as diameter. So now if I take the focal length as diameter and I draw a circle. So this circle should be touching my tangent at the vertex. This is what I need to prove by this property. So it doesn't matter where do I take it. Okay, it is true for any goddamn parabola. So the same thing can be done if I have a parabola even here. Okay. Or it could be anywhere. It doesn't matter. Because when the property is true in the standard one, it can be extended to the general system. Let's say I have a parabola this way. And someone has given that this is my focal distance. Now, if I just draw this parabola, then I'll be having here tangent at the vertex. So this circle will touch the tangent at the vertex if I draw considering focal distance as diameter. This is what we have to prove. So moving ahead. So that's what I have here. Now you consider this parabola to be y square is equal to 4ax, our standard parabola. Now this point, I know it's going to be what? A comma 0. And since this is any point on the parabola, this one is any point on the parabola. So you can consider this point to be what? 80 square comma 280. We'll consider the parametric form just to be on the safe side. So we always have been considering the parametric form. That's better. Now I have this point is lying on the parabola. In fact, since this line is serving as the diameter for my circle, that means I can take this point to be P and this is S. So we can get the equation of circle. So we can have the equation of circle. So we can have the equation of circle passing through, circle having S and P as the endpoints of diameter. As the endpoints of diameter. It's called diametric form of circle. We can use the fact diametric form of circle. So diametric form of circle is what? If two endpoints of the diameter are given. So I say x minus x1 into x minus x2, and then plus y minus y1 into y1, y minus y2 is equal to 0. This is my diametric form. Now I can simply apply this to get the equation of this circle. And then since I have to prove that this touches at the tangent at the vertex, so I'll be writing the equation of tangent at the vertex and then solve with this circle. And I have to show that this has only one common solution. Now what happens? So x minus x1, you can take a, and then next one is going to be x minus x2 is what? At square. So we can write down here this plus y minus y1 is 0, and then again y minus 2at is equal to 0. Now, this is the equation of circle, okay, which I'll leave it as it is because we should not be modifying this further. Ultimately, most of the terms are going to get cancelled. Now, solving with the tangent at the vertex. So, solving with the tangent at the vertex. Solving with the tangent at the vertex. So, tangent at the vertex. This line is what basically it's touching the parabola at the vertex. That's why it's called as the tangent at the vertex. We'll discuss this more precisely in the tangency, which is our upcoming topic. So solving with the tangent of the vertex, this equation is what? This is my line y-axis here. So this is x is equal to 0. X is equal to 0. Now I'll have this equation 1 and this is my equation 2. So solving equation 1 and 2 together. So solving equation 1 and 2 together. So which is same as just putting x is equal to 0 into this equation 1 because we are solving these two together. So I'll be having here x is equal to 0 when I plug in. So I'll be having 0 minus a into, please let me write down my standard a. So 0 minus a into 0 minus a t square plus y minus 0 into y minus 2at is equal to 0. And this is what we have got. Yeah. And now let's open this. So this turns out to be basically a square t square plus, if I multiply here, so I'll be having here y square minus 2 yat is equal to 0. This can be further written as what? Y minus at the whole square is equal to 0. It is enough to say that I have drawn a 2-degree curve with a 1-degree line, and I'm getting only one solution, which means this is a tangent. So this implies the line x is equal to 0 is a tangent to the circle. Is a tangent to the circle. Now this circle having SP as diameter. Circle having SP as diameter. In fact, now we know also the point of contact. Also the point of contact. We know the point of contact since x is equal to 0 there, so you can just plug in 0, and then y is what basically at. So the point of contact is 0, at. So this was again a very important property. In fact, you can derive another similar result. So this is fourth one. So here I have drawn a circle considering focal length as diameter. However, if I consider this entire focal chord only as diameter, okay. So let's check the fifth one. So I am saying that circle drawn considering focal chord as diameter. Circle drawn considering focal chord as diameter touches the directrix. Touches the directrix of the parabola. Let's see this result. So I have circle drawn considering focal chord as diameter. So this is almost same as this thing. The only task is I'll be having a parabola here. And this is my focal chord. Now I'm drawing a circle considering this focal chord as diameter. Let's think the insane circle. Like this. So now this will touch the directrix. This will touch the directrix. Now, see, don't be influenced by my diagram because it feels that this is touching exactly at the foot of the directrix on the axis, but That need not be true always because it might touch here also. It depends what kind of focal chord I have. Now let's see. Let's prove this one also. So I know from this result that this is my point a comma 80 square comma 280. So if I know what end of the focal chord, then other end I know. Other end is basically a by t square comma minus 280. This one I know. So now I have to prove that I anyhow have to get the equation of this circle. So let's go ahead. Again, we will use the diametric form because say this is point P, this is point Q, and this turns out to be S. So one should not be taking this S to be the center because that's nowhere mentioned. So equation of circle with PQ as diameter. With PQ as diameter. Again, we can use the diametric form. So I have here x minus at square, comma, x minus a over t square, and then plus y minus 280 into y plus 280. This is equal to 0. And and equation of directrix for this parabola. This is my standard one, of course. Y square is equal to 4ax because these are the parametric points, so which are for the standard parabola. And then I have the equation of directrix, which is x plus a is equal to 0, which means x is equal to minus a. So again, we can work on the same principle that I'll be taking my circle and I'll be solving with this line. So I should get only one common point. Or say better to say one common solution, only one common solution. So it will be tangent. So I'll be just plugging x is equal to minus a here. So open this. Minus a t square into minus a over t square plus y square minus 4a t square is equal to 0. So if I take minus common, in fact a also common, then this everything gets cancelled. Just leaves me a square. And then this turns out to be 1 plus t square into 1 plus 1 upon t square. And then plus y square minus 4a t square is equal to 0. So moving to the next page, this will be a square into 1 plus. I'm multiplying these two terms together. So 1 plus 1 by t square plus t square plus 1. So 1 plus 1 by t square plus t square plus 1. Then plus y square minus 4t square. So plus y square minus 4a t square is equal to 0. Now this thing turns out to be a square into this is t square plus 1 by t square plus 2, which can be written as t plus 1 by t, the whole square. So this is t plus 1 by t, the whole square. T plus 1 by t, the whole square. And then again plus y square minus 4a t square is equal to 0. Now this could be written as further. This written as a square. Wait a moment, this is not turning into a perfect square. It is square comma 280. Oh, here there is a problem. This should be 2a over t. So this entire portion became incorrect. This portion is incorrect. This turns out to be minus t over t because we know t1 into t2 is minus 1. So this is basically minus 2a over t. So it will become 2a over t. Now if I multiply, so I'll be having here y square, then plus 2a by t into y by t into y, and then minus 2at into y minus 4a square is equal to 0. Now let's move further. So this can be multiplied. No, even this part is also incorrect. Hmm. Now if I multiply here, so I can see here everywhere it's a present, so I can divide by a in fact. And this will give me simply 1 plus t square into 1 plus 1 by t square plus this guy doesn't have a, so I can just keep it here because there is no point. And then this would be basically y square. And then I have here, I'll be taking 2a outside. So this gives me 1 over t minus 1 minus t into y minus 4a square is equal to 0. Now we can multiply and rewrite this equation. And this gives me why they are looking paralyzed. Okay, no problem. Ultimately, we have to multiply. So a into, let's multiply them. So 1 plus t square plus 1 over t square plus 1 plus y square. This is plus, yes, y square plus 2a times 1 by t minus t into y minus 4a square is equal to 0. So we can expand this now further. And this could be written as a into, this is t square plus 1 over t. But since this is 1 over t, so I'll be writing here rather t minus 1 over t the whole square. And now minus 2a I'll be subtracting here. So this turns out to be basically a into t minus 1 over t the whole square. And then this would be y square. One part is going to be subtracted here. So I'm writing here y square. And then I'll take minus common here. So I'll be writing here 2a times t minus 1 over t into y. And then the leftovers are going to be balanced from here and then the last one. So I'll be balancing it. So far I have balanced y square and this is balanced. This guy is also balanced. Minus 4a square. So this is 2a. This part is basically t plus 1 by t the whole square. So which we are writing t minus 1 over t the whole square and then minus 4a. Minus 2 minus plus 4a. This could be balanced here, so I have here 4a. So yeah, this is 4a square. Yes. Hmm. I think some calculation error is there here. Mhm. So we can see here everything is balanced. So this is y square. This 4a. This part we have taken out here. So that is a into a will be a square. A square, a square, a square. Now plus 4a square and this minus 4a square gets cancelled. So we get basically y square minus 2a into t minus 1 by t into y plus a square into t minus 1 by t the whole square is equal to 0. Now this is nothing but a perfect square of y minus a into t minus 1 by t the whole square is equal to 0. So this implies x is equal to minus a is a tangent to the circle. This property also we have established. The circle drawn considering focal chord as diameter touches the directrix of the parabola. Now, move to the next part. Next part is property number 6 of the parabola. So the focal chord. The length of the focal chord of the parabola y square equal to 4ax, making an angle theta with the x-axis is 4a cosec square theta. So that means I have a parabola here, and then I have the focal chord of the parabola. So this is my focal chord passing through the focus, and this makes angle theta with the x-axis. So I want to find out the length of this focal chord. So Let's see how do we do it. So length of the focal chord we'll find out. For this, we'll just take a point here. This point I know it's a comma 0, and this point I'll be taking it 80 square comma 280. Say this is S and this is B. So we can write down here, and this turns out to be slope of S is basically what? So 280 over 80 square minus A. So this could be written as A gets cancelled, you get 2t over t square minus 1. So we'll keep it. Now slope is also given by, since this is the angle here, it makes angle theta with the x-axis. So I can write down tan theta. It's also nothing but slope only. So tan theta, I know it's going to be what? 2t over t square minus 1. And now if we see here, so length of the focal chord. So length of the focal chord, we already have derived along that, is a into t plus 1 by t, the whole square. Is the length of the focal chord. It was derived in the lecture 3. Now, so if I consider this part, a into t plus 1 for t square, and then all I need to do is just convert this entire length of the focal chord into tan. So I get one result here. So let's go ahead. Now, so length of focal chord is yeah, so tan theta is 2t over t square minus 1. So this part, I need to plug in t here in any form here. So better, I'll just take here 2. So I'll be having tan theta over 2 is equal to t over t square minus 1. Since I want to use t minus 1 over t minus 1 over t, so I'll take the reciprocal of this guy. So I'll be having t square minus 1 over t is equal to 2 by tan theta, which is nothing but 2 cot theta. This could be written as t minus 1 over t. So this is t minus 1 over t is equal to 2 into cot theta. Now, this is nothing but a, and then I can write down here t square plus 1 over t square plus 2, which can further be written as a into this is t minus 1 over t, the whole square. Now this will be what? T square plus 1 over t square minus 2. So I'll be writing here minus 2 and then plus 2 will be gone. So minus 2 and plus 2 will be gone. So this is simply a into t minus 1 over t is 2 cot theta. So we can just simply square it and write down 4 cot square theta. Oh, I guess wait a second. A into t plus 1 by t is the length of focal chord. So t plus 1 by t square, this is t square plus 1 over t square plus 2. Yes, perfect. This can be written as t minus 1 over t square. So t square plus 1 over t square minus 2. So, oh, sorry, that's plus 2 basically, not minus 2. We already have a minus plus 2, and then already we have plus 2. So this turns out to be a into 4 plus t minus 1 over t square is 4 cot square theta. So you can take 4 common. You can take 4 common. Wait a moment, I'll do it on the next page, in fact. This could be written as is equal to a 4 common, a common, and 1 plus cot square theta, which indeed is nothing but 4a cosec square theta. So this is what we had to prove, that the length of the focal chord of a parabola y square equal to 4x, making an angle theta with the x-axis is 4a cosecant square theta. And that's what we proved. We have another property in the row. The length of the line segment joining the vertex of the parabola y square equal to 4x, and a point of the parabola where the line segment making an angle theta with the x-axis is 4a cot theta into cosecant square theta. So we need to understand what this theorem is saying. That means what? I have a parabola like this. So the length of the line segment joining the vertex, that means from here to here. This is the length of the line segment joining the vertex of the parabola and a point of the parabola, where the line segment makes angle theta here. This one. So these properties are very helpful in solving the problem later on. Okay, so first we will derive all these things and then we will go ahead. So this is 0, comma 0. This makes angle theta with the x-axis. So I want to find out this length. So this is point E. So I am finding this distance, VP. My goal is to find out VP. So let's see how can we do it. So of course we'll go for the slope. So slope of VP is basically what? Theta. And if I take a point here, so theta, tan theta. Yeah, this point is what? 80 square comma 280 again. So if I find a slope, so also slope of vertex with this point is nothing but 280 over 8t square, which indeed turns out to be 2 over t. Which is nothing but 2 over t. That means now I know what is t value. So t value is going to be basically t over 2 over t is nothing but tan theta. So t is equal to 2 cot theta. T is equal to 2 cot theta. So we can just plug in here t directly. So therefore, vertex V is 0, 0. Vertex V is 0, 0. V is 0, 0. And P becomes T we have. So this turns out to be 4A t square. That means I'll be having cot square theta and 280 means 4A cot theta. Now, I want to find out VP. So can simply apply distance formula. So distance formula will give me this is 0, 0. That means if I subtract it here and subtract this one here, so there is not a big difference. We can simply write down here 4a cot square theta. This will be 4a cot square theta, the whole square, plus this part is 4a cot theta whole square. So 4a cot theta whole square. So we can keep 4a outside completely, and also in fact cot theta outside with modulus. And then inside we have here this cot theta and 4a are common. So I'm left with only 1 plus this is now cot square theta. So this is 4a cot theta into cosecant theta. So this is the length of the line segment, VP, or say OP, whatever you would like to call. Hmm. Then we now come to tangency. This is the most crunchy part of the entire conics. Okay, tangency. That means what? Say I have a line here and I have a parabola. I have a line and I have parabola, so only two things are possible. Either this line L will intersect the parabola, so I can add on here y is equal to mx plus c be the equation of line, and I have this parabola, so either L might intersect, L might intersect, or it might touch, or it won't touch. So these are the only three possibilities for a line with parabola. So again, we'll apply the condition. So let y square is equal to 4ax be a parabola. And I have, and y is equal to mx plus c be a line. So now we can just simply plug in here. So we'll solve these two equations. And since this is a 2-degree conic, okay, so for a 2-degree conic, if I have a line and I just solve this line with the given conic, I get a quadratic equation. So for tangency, if I solve for b square, the discriminant b square minus 4 is equal to 0 as in the previous case. So it ends up proving that it's a tangent. So we can go ahead and just solve line and parabola. Solving line and parabola. This ends up giving mx plus c the whole square is equal to ax. Open this thing. So m square x square plus 2mx c plus c square is equal to 4ax. We can just bring it here. So m square x square plus 2mc minus 4a into x plus c square is equal to 0. Now, this is a quadratic in x, so I'm going to have two solutions, but since I want b square minus 4ac, so let's find b square minus 4ac. This comes out to be 2mc minus 4a the whole square minus 4m square c square. So open this thing, this is 4m square c square minus 2 into 2 into 4 is 16mca. 16mca plus 16a square and then minus 4m square c square. This also gets cancelled. That means now I have b square minus 4ac. So b square minus 4ac turns out to be 16a square minus 16mca. 16a square minus 16mca. So now, if b square minus 4ac is positive, so this implies it will have two solutions. So it would have two solutions. So if it has two solutions, this implies line L would intersect the parabola. Line L would intersect the parabola. And if b square minus 4ac is negative, that means line L won't touch the parabola. Line L won't touch the parabola. And if b square minus 4ac is 0, then line L will be the tangent. Line L will be the tangent to the parabola. Now let's see. So b square minus 4ac is this guy. That means I have to solve for 16a square is equal to 16mca. So of course I can cancel 16, 16, and since a is non-zero, so this also gets cancelled. That means I get c is equal to a over m. This is the required condition of tangency. So the required condition of tangency is c is equal to a over m. And the equation of line would be the equation of line, or it's the equation of tangent, better, is y is equal to mx plus a over m. So this is the equation of tangent to the parabola having slope m. Okay, so equation of tangent to the parabola having slope m. The equation of tangent to the parabola having slope m is this: y is equal to mx plus a over m. Now I'll be writing a note here. So what if my parabola is shifted? So for a shifted parabola, that means if my parabola is y minus k square is equal to 4a into x minus h. So the equation of tangent, so the equation of tangent having slope m is, we know the real method, we have to call y minus k is equal to capital Y and small x minus h is equal to capital X, and just simply at the end add this shift hk. So I can write down now y minus k is equal to m into x minus h plus a by m. So this is the required equation of tangent when my parabola is shifted. Now this is the equation of tangent to the parabola having slope m, and we know the condition of tangency. Now let's write the equation of tangent to the parabola at a point. So now equation of tangent to the parabola. So equation of tangent to the parabola at a point P. x1, y1 on it. X1, y1 on it. That means what? I have a parabola, and now this is my point P, say x1, y1, and I want a tangent to this parabola at this point. So what is the equation of tangent at this point? To find the equation of tangent at this point, okay, we just need a slope and the point. So I already have the point. That means if I get the slope at this point, I'm done. So we have y square is equal to 4ax. We'll differentiate this with respect to x. So differentiate with respect to x will give me 2y. dy over dx is equal to 4a. So I know my dy by dx will be this 2 gets cancelled. So yeah, 2a over y. So now I want slope at this point. So therefore, dy by dx at x is equal to, no, not x is equal to at point P. Slope at the point x1, y1 is going to be 2a over y1. It's going to be 2a over y1. So now I have the slope at the point. So by slope point form, I get the equation of tangent. So by slope point form, the equation of tangent would be, so y minus y1 is equal to slope is 2a over y1 into x minus x1. Now I can multiply it here. So I'll be having y1 minus y1 square is equal to 2ax minus 2ax1. Now since x1, y1 lies on the parabola, x1, y1 lies on the parabola. So this implies y1 square is equal to 4ax1. So I can now write down y1 is equal to, so it will be 2ax, and this guy would come here and we'll make it 2ax1. So this becomes y1 is equal to 2a into x plus x1. So y1 is equal to 2a into x plus x1. This is the equation of tangent to the parabola at a point P on it. Now, tangent in parametric form. So tangent in parametric form. So we now know already this is x plus y1. So the point is 80 square comma 280. So I'm now going to have y1 is equal to m. It's 2a into x plus a t square. So this 2 into a gets cancelled. And I get yt is equal to x plus a t square. Now, in fact, one can gain tangent from here also without solving the tangency. If you write down here, y is equal to, say if I write down 1 over t into x plus at. So if I compare with, y is equal to mx plus c. So I get 1 over t is equal to m and c is equal to at. So t is equal to 1 over m. You can just plug in here. So c is equal to a over m. This is the condition of tangency. You can even get it from here. So condition of tangency can be derived even from the tangent at a point using the parametric form. This parametric form actually represents the entire parabola. So now we know the equation of tangent for both the parabolas. If my parabola is not shifted, I have this. This is the condition of tangency. If my parabola is shifted, then the equation of tangent to the parabola is this. And this is for equation of tangent to the parabola at a point. Equation of tangent to the parabola at a point. So y1 is equal to 2a into x plus x1. Now moving further. For the parabola, x square is equal to 4by. Now we're going to have the tangent for this. So x square is equal to 4by. And the same story would continue. So instead of deriving that long proof, we'll just simply go for the equation of tangent to the parabola, and from this we'll get the condition of tangency. So let's go ahead. This is my parabola x square is equal to 4by. And now we can take any point on this. So our goal is now to get the equation of tangent, no, to get the condition of tangency first. So to get the condition of tangency, and after this, equation of tangent at point P, at point P, and equation of tangent having slope m. So this is our goal. That means three things we need to find out: condition of tangency, equation of tangent at P, and equation of tangent having slope m. So let's go ahead. So this point I'll parameterize it. So y is basically pt square, comma, this is 2bt. So let's write on the equation of tangent. So we can differentiate this. We have x square is equal to 4by. So we have here 2x is equal to 4b dy over dx. So therefore, slope at the point dy by dx at p would be equal to uh, going to be equal to be 2x 1, or I mean not 2x 1, x point I have already. So this is 2bt. X is 2bt on 4b. So dy over dx at point P is going to be 2x over 4b. So x is nothing but my 2bt. So now I get 4b, 4b gets cancelled. I get the equation of, slope to be t. So therefore, equation of tangent. So therefore, equation of tangent can be drawn at point P is basically y minus bt square is equal to slope is t here, and then x minus 2bt. X minus 2bt. That's the equation of tangent at point P. Now also we'll now see here, so y is equal to, this is dx, and then I have here minus 2b t square minus, no, plus bt square. So this turns out to be y is equal to dx and minus bt square. So if I compare with y is equal to mx plus c, so I get my m is equal to t and c is equal to minus bt square. So therefore, c is equal to minus pm square. This is the condition of tangency for the parabola x square is equal to 4by. So this is the condition of tangency for x square is equal to 4by. And this is the equation of tangent. We can write down like this also. We can write down this way also. Now, so we now derive the equation. Oh, of course, we'll add one more point. So if the parabola is shifted, so the parabola is shifted, say my parabola is now x minus h square is equal to 4b into y minus k. So then equation of tangent would be y minus k is equal to t into x minus h, y, oh, yeah, y minus k is equal to t into x minus h, and then minus b t square. But if my parabola is shifted, then these are not my ordinary points. So I cannot directly replace it. Instead, I recommend you to take the parametric form and then make proper substitution accordingly. Make the proper substitution using this point. In fact, now we know my parabola is shifted, so I know how to find the equation of tangent. So you can just simply start writing here y minus k is equal to t into x minus h, then minus bt squared. But then these are not my parametric points. Or if you just write down the original parametric points, that is also correct, no problem. So far we now have only the equation of tangent in this session. Oh, we will stop now. We'll see you again with more problems, and problems based on the tangent and the properties of the focal chord in the next session. Stay tuned. Thank you so much.